just from its construction. But we have now the problem that we need to set up something from observations. And this is how to do that now. Yeah? And this is then something that we would need to take into account. Even if you take some atlas about the brain, you will probably find something and you say, oh, it looks like this, looks like this, looks like this. But we also have to take into account that there are many, many, many structural alterations of the brain that are associated with epilepsy in whatever manner. If you ask, is this the reason or is this the cause? This is the question for the hen and the egg. Yeah? So there might be something, you see a patient after 25 years of epilepsy and you see also that there is some structural modification in the brain. You don't really know what is the cause and what is the effect. So that would need to be taken into account. Yeah? This high variability. And then comes the other variability from the functional side, that you have dynamics that go from something that is completely normal to occasional events where you have such a kind of an activity where the brain goes into some kind of an extreme event state and comes back. Yeah? So how can we derive a network from that? And what kind of network, and how to do that, and from which kind of observations? The idea for that was, of course, triggered by the famous work by Watts and Strogatz in 1998, when they set up some idea to generate something between randomness and structuredness. So between a lattice and a random network. And that was the idea to introduce some kind of a rewiring scheme where you start from a lattice-like structure and then you rewire some links and then you end up with something that looks something in between. And this something in between was then a big hype because everybody now says, okay, now we can explain probably the world, apart from, and now I jump back from partial differential equations to stochastic partial differential equations, but something in between for which we do not even have mathematics, except for you go to graph theory. Yeah? And then the idea was then, if we have something like that, and now we can try to merge something that has been split in the Middle Ages, namely studies of structure and function, not or. Yeah? This is exactly what we have in the natural sciences, that we have either structure or function, but there is nothing in between that captures both. And that would be the idea here, that we can tackle this, this structure-function relationship again and see what can we learn from such an approach. Yeah? Now this is an ongoing research. It's not just the dynamics of networks. We had this last week, networks of oscillators, what they can do. But you can also consider what will happen if these networks evolve in time, in some kind of a strange way, where nodes pop up and links pop up and they go away and they come back, and some kind of a reorganization of these networks. And then, of course, then the level of networks of networks of networks. And that is, of course, extremely sexy for the brain. If you think in terms of I have a neuron and you would consider this as a node, and then you have a neuronal pool, and this is then some kind of a small network, and this is then sitting in a bigger network, and that makes up the whole brain. Yeah? This is hard work, but it's worth doing that. Just a brief reminder. You know that. Everybody knows that. Yeah? A network is a set of links and a set of nodes. And that comes in different flavors. It could be a binary network. That means that the link that connects two nodes exists or not. Or it carries some information, like weight or end direction. Yeah? And then from graph theory, you have many, many ways to characterize these networks from the level of a single ingredient, so from the node or from a link, up to the complete network. Go to textbooks on graph theory, you will find tons of different things that you can do with networks. Yeah? The question is, what does this tell us? If you assign to a network that you have derived from the brain, you assign a clustering coefficient, and you find 3.1415. What does this mean? How to translate that? How to bring this in the context of physiology, in medicine, or whatever field of application you have? Yeah? This is the current task that is being done. Try to map characteristics for networks onto something that you know already. And then see, is there something new? Is there something that just replicates something that is known already? Or do we really gain new information on that? Yeah? So many, many ways to do that. You can start from the single level nodes or edges. You can ask for the influence or the importance of something, which is also important later on for the network, up to clustering coefficient, the path lengths. And then you can also ask something like stability or robustness against perturbations, whatever. And then there's also the intermediate level, which is kind of hard to do, because there are many, many approaches in order to define something like what is actually a community of something. Yeah? So once you have that, this is graph theory, you can start and set up your network. The question is how? Yeah? Why this is, and why it is sexy, is this distinction. Yeah? We have on the top, we have something that is regular, and on the other part of the spectrum, we have something that is completely random, and then we have these complex networks in between. And this in between is exactly what we would like to identify, because the world above, this has been done. Yeah? This is any kind of modeling that you do in terms of mean field approximations of brain dynamics down to single neurons, and you put them together onto some random network. But the question is, what is going on in between? Can we learn something from observations of what is this in between? That would be the idea. Good, let's do it. We have to choose a scale if we go for structural networks. What do you want? And what can you assess? If you start from the level of nodes and links, probably no chance. Or maybe not yet. Or maybe at the end of your lifetime, not of mine. Yeah? This is something, it is desirable, but it's extremely hard to assess. So all these 10 to whatever neurons or cells, if we take also into account other types of cells, together with their connections. This is something that would be needed. On the large scale, we have, of course, some techniques. They have their pros, they have many cons, something that you would need to take into account. So go also into the details of these different measurement techniques. You would need to ask, what can you really do with these? Many people just trust that, for example, DTI is the way to study the structure of the network. It misses lots of information just because you're studying tensors. Yeah? Something that you can't capture, not in the living brain, unless you freeze it and then you do measurements that run over weeks. Okay, you can do that. Medium scale. Does anybody know how to assess the medium scale? Me neither. Something that is missing. Yeah? If we go to function, we have exactly the same problem. We can measure with single electrodes designed for whatever, you can assess the dynamics of a single node. A few of them. Hidden mentioned something like 1,000. This is what we currently have. So orders of magnitude away from the full structure, the full dynamics that we can access with that. If you ask, can you measure the dynamics of a link, so a synapse? Yes, yeah, maybe, under these and these constraints, yes. Yeah? Take into account, these are experiments being done in slice. You have strange boundary conditions, very strange boundary conditions. Don't wonder that you see some kind of patterns that are just due to boundary conditions. It has nothing to do with the true dynamics. Hilda, yeah.
My question is, everybody looks at these networks as being bidimensional. Mm-hmm. So, are they truly? Are all these networks? Do we know if the neurons are indeed on a bidimensional?
It's an approximation. Yeah. How well this is, no idea. Yeah. Keep it. You will have more questions. Good, so there's something that maybe allows you, this is emerging technology, Nitin was talking about that. We talk about electromagnetic waves. Yeah? Whatever else is important in the brain, this is currently under investigation. Large scale, okay. What is a node in the large scale? The easiest thing to do that is either say, I measure the collective information from a bunch of neurons, and then you assign typically a node to your sensor. That could be an electrode, that could be some kind of a coil, that could be a voxel in fMRI, that could be whatever. Yeah? This is the typical assignment that is done, and it sounds reasonable, right? Because everybody does it. Everybody does it. What is a link? An interaction. We are interacting. I am now the driver, you are the responders, hopefully. And there's somebody outside that needs to identify what is the strength of the interaction, what is the direction of the interaction, what is the functional form, from observations. How to do that? Without perturbing the system. We need observations, we need time series analysis. We come back to that point. Yeah? So this is something that is then being done. Now, again, medium scale, what is this? Can we assess that? No. So we are at the extremes of these networks of networks of networks. We can go down to the micros, but the most elementary thing, up to the whole structure. And then the approach is then typically something like that. If you go from measuring interactions, you have some dynamics that you have measured from different recording sites, from different nodes. You set up some interaction matrix. Matrices always look nice. You have some idea about what that could mean, if they are stable or not. You may ask many, many questions about that. And then it's mostly an idea of what kind of graph theoretical approaches do you need? Is this only for binary networks? Is this something that is allowed also for weighted networks? You can stay on the left side, or if you only believe in, would like to work with binary networks, you need to find something that maps this interaction network to an adjacency matrix, which is also the left one, yeah, but for a weighted style. Good. You might know these definitions. Yeah, this is something that emerged from fMRI study, where people talk about the structural connectivity and the functional connectivity and the effective connectivity. Everything is based effectively on correlations. We are talking here about dynamics. Correlation means you are studying amplitude relationships. If we talk in terms of we have some kind of synchronization phenomena, the amplitude might be completely irrelevant. There are many, many systems where you do not see anything in the amplitude relationships, but you see it in the phase. And if you don't see it in the phase, you would need to go to other concepts of synchronization. For example, generalized synchronization. We will come back to that. Yeah? Structural connectivity, this is exactly what we don't have access to. That would be the cabling in the brain. Effective connectivity means you have some way to assess a directionality of an information flow. And this is typically done with Granger causality that has pros and cons, but it makes many, many, many assumptions. And there are other ways to do that. But people stick to that because it is in the toolboxes. So, accessibility is one thing. We know that there are limited methodologies. We have this functional connectivity. You need to ask what is actually a good measure to study that. And if you go for effective, you would need to define what is actually a coupling in the brain. This is everything that is relying upon that. We need to understand what is that. Yeah? Good. So, we go into details now. We have this idea, we have this set of nodes connected by links, we have some kind of a representation, and then we know that there are many, many approaches to characterize that. And then you make the ansatz that you say a node and a link is either associated, it is not exactly the same, it is associated with a measurement position or a sensor, and the link is an interaction between the subsystems. Between the subsystems, you take that for granted, right? We'll see if that works. What we have here mathematically is an inverse problem. Helmholtz, 1800 something. The inverse problem has no unique solution, period. Good. What we do is an approximation. We need to ask how well can we do that. Good. These are some challenges which I would like to discuss in the next few minutes. If we try to identify nodes. If you recall my first talk, not on the seminar, but the other one, we had already the issue from the very beginning, how do we sample? Why do you go in the fMRI for voxels and you take some 3D space and you distribute this equally? Or why do you place electrodes in a sense like you do that? Or why do you place MEG coils as you do that? Nobody questions that. You will see what is going on there. So some kind of a discretization of the space. The same then for for the link identification. We would need to do some kind of a temporal sampling. What is a good sampling? You go for textbooks, you will find Wiener-Kinchen theorem that tells you something. Good. Nyquist theorem tells you also something. How? If you have a bunch of different types of dynamics. Oversampling might be okay, but we will see it's not okay. There might be direct interactions, but there could also be some kind of an indirect interactions. Indirect because you have not observed that. Indirect because you have some kind of an bias that is being introduced just because of your measurement technique. People who work with EEG know that it's a crucial thing to choose the reference electrode. Yeah? And if you say, I do that because somebody did that, yeah, this is done because for exactly this approach what the other guy does. If this is also something good for you, you need to check that. So, how reliable are these? How can you measure reliability of that? Take into account, you have maybe in the real worst case scenario is you have one shot and nothing else. There's nothing to average or whatever. This is only the data that you have and you have to live with that. How to do that? And then you found something. Then you need to compare. You need to compare data, networks, characteristics of networks with another network. You will see that there is nothing available even from graph theory so far. Good. First point. You have a spatially extended system. If you say we study interactions, what you implicitly assume is that you can decompose the system into subsystems. Who tells you what are the subsystems of the brain? How do you do that? Take climate. What are subsystems of the climate? This is the implicit assumption. And from that, you place sensors. From this assumption, you go and place sensors. Is this assumption correct? Ask yourself what you are doing there. Yeah? So, is this justified? If it's justified, if you have good arguments to do that, even if you say everybody does that, okay. Now, what is an optimum sampling of these subsystems? It could be that even the size of the subsystem might be different and you end up with a non-homogeneous sampling. Okay, there are techniques for that. You would need to take this into account. Don't just do a constant discretization and assume everything is the same. Yeah. You don't know the spatial organization of these subsystems. So you need to have either some kind of a good educated guess or somebody tells you how to do that. And if not, then you say, okay, let's go for some rectangular arrangement because the experimentalists always do that. Good. Be aware that this could be a source of error. I will show you some examples for that. What is a good distance between them? You have a sensor that typically captures the dynamics of just one subsystem. If you place this in a non-correct way, you might see some kind of an overlap. So one sensor measures the dynamics of two subsystems. Can you distinguish that afterwards? That introduces correlations. Okay, and then accuracy, reproducibility of such a measurement. If you go for fMRI, they currently experience some crisis because nothing is reproducible. Why? That was a study that we did already because we observed that in many, many fields of science, you observe small words. And you ask, why? Why do we have small words there? Brain activity. You measure the MEG, so the magnetic field of the brain, during some resting condition. And then you estimate the clustering coefficient and the path length, and you find these values there. Clustering coefficient 0.5 and path length 3 point something. Now we came up with the idea, what is the arrangement of the sensors? It starts in the middle and it goes concentric around the head. Again, some kind of a structured placement of sensors. You make a spatial model, like there, a very simple one. You have an exponential decrease. The activity is dying out exponentially. In this model, there is no dynamics. This is just this model. You set up a network like that, and then you get these values for the clustering coefficient and the path length. Where's the dynamics? Is there a reflection of the dynamics in these values? You need to distinguish that. We have this system. This is our subsystem. No, this is the system. Now we decompose this into subsystem, and then we ask, there's some kind of connection between them. We place a sensor here, and then we have a network, and then we say, okay, we can measure the interaction between them, and then we characterize this with the clustering coefficient, with the path length, with assortativity, whatever is your favorite measure for that. Yeah? Good. Let's assume we have something like that, namely a bias in the measurement. That would introduce spurious links between this greenish sensor, this greenish node, and the other ones. If you do this in both, if you have something like a common bias background, you will set up a network like what is shown up there. You don't know what is green and what is blue. You only see links, and you need to ask, is this true or not? Yeah? So what we did was we simulated that by a simple model. We keep these systems like they are, but we do some kind of an inheritance of nodes. Yeah? We take more nodes than there are. So we have effectively, if we do it like this, we consider this as if we have 2 times n sensors that sample exactly the same. Sensors are exactly the same. If you do that, you find that the clustering coefficient is always larger or equal to the one that you would have. The path length is more or less the same because the distance between the sensors vanishes. This is the model that we have. And the assortativity increases. So even if you have a disassortative network, you might end up with an assortative one. Go to the literature, you will find that most of the brain data is assortative. Why? Not just because the brain is assortative, it could be just an effect of the measurement. In that sense, even if you have a random network, it will look like a small world. Even if you have a disassortative network, it will look like an assortative one, if you don't take that into account. So, just one example. There are many, many other ways that you need to take into account when you do this association between nodes and sensors. A wrong spatial sampling can lead to a mischaracterization of these properties. Now you need to ask what is better. I cannot give you an answer here because that depends on the system that you have. Something that you should take into account when you study networks, what is a good approach to that? Yeah? We go to link. First one, do you have good observables? I don't touch upon that because we had this so many times. Yeah? We assume that the EEG is something that makes sense for the brain. Good. We sampled something in time. Yeah? We have this Nyquist-Chen theorem, Then we need to measure interactions, and we would also need to take into account that there are many, many confounders. I will show you some of them that are there, that are relevant. Fortunately, the temporal sampling can be corrected for if you have null models, or if you have some kind of an idea of how to resample that. This was also a study that we did on interaction networks, and for that one, we developed some kind of tailored random networks. So we go to the other extreme to say if we see a deviation from the case that we have a true random network, then we are sure, or almost sure, that we can say there is some kind of, that makes sense. You could also go for the other extreme and make this relative to a lattice. There are some approaches available. These are the standard null models from graph theory, but you would probably need something else. So we have that one here. We have some time series, some amplitude over time, and this is, let's assume that this is the true one that we have, and we need to make some choice, namely the observation time. So how long do we measure something in order to capture the relevant dynamics? And the sampling frequency, and then that determines the length of the time series, and with that one you have already then the interplay between stationarity, non-stationarity, accuracy of something that you do. That is some kind of a balance that you would need to make, again, depending on your system. Let's assume we sample like that. No, this is a tiny zoom, what is shown up there, and now we have some data points. This is the data that you have. Yeah? You could also do something like that, just to make sure that you capture everything. You do temporal oversampling. Yeah? You have enough disk space, why not? Yeah? Let's do it. That induces temporal correlations. So again, some model, we generate 100 time series, some random time series. We do this with 500 points. You see, this is just some random data. We introduce some kind of temporal correlations in the data by using a moving average of size m, a low-pass filter. Something that you always need to do in order to band limit your data. Yeah? So the signal interdependence, we do this here now with the correlation coefficient, just to show what is going on. That affects almost any other measure, irrespective of what you do. This is a general problem. And then we derive networks from these. So we have a bunch of these recordings. And now we go for a binary representation. And we use a link. This is a fixed thresholding such that the link density is always 0.1. Yeah? Just to make comparability between the networks. If you study cluster coefficient and path length in dependence on the amount of correlations that you introduce, so in that case, the size of the moving window, then you see that they increase the more correlations you have. There's some famous theorem that says you compare the clustering coefficient against the one that you would get for a random network, and if you take the path length and you compare that to a random network, and if this ratio is either larger or smaller than 2, then you have an indication for a small world, which is exactly in this blue rectangle. This is the whole area of small worlds that you can observe from a random network with random data just because you introduce correlations. And assortativity, unfortunately, is the same. You go from a disassortative to an assortative network. Take into account that just simple things like sampling can make specific types of networks, irrespective of the dynamics that you have. Good. We go for identification of links. We would need to measure something. Measure interactions. Either you do this in some kind of a probing way, that would be some kind of an active experiment. This is what you typically do. Let's assume you can't do that. You would need to have some kind of an observation. Then you have a large amount of data. You need to tackle the problem of non-stationarity. On the other hand, if you do probing, you can do repetitions, you can take averages if you're allowed to do that. And you need to question, is this what you are measuring really the true dynamics? Because this is nothing else but response functions. Okay? Perturb the network, let it relax. Good. If you do observation, I mentioned it already, you would like to have something like the strength, the direction, and the coupling function. If you ask people that develop time series analysis techniques, this is a Swiss Army knife. Nobody has that. We have now one approach, that allows you to identify all these different characteristics of a coupling, which is based on phase relationships. Anything else is not yet available. People are working on that. Namely on that part here. Yeah? So you assume that you have some kind of synchronization between the different systems, the different subsystems, and from measurement of a synchronization, you go back and say, this is a characteristic of an interaction. This is the idea behind that. Yeah? That requires, of course, that you have some kind of an oscillatory motion, self-sustained oscillatory motion. Either you give some energy to the system or you push energy into the system. That is probably something that you have in the brain. It also requires that you have weak couplings. Because all the techniques that have been developed assume that you go into the weak coupling range. Strong coupling is something that you can't even observe in nature. Really strong coupling. I mean, not even during the seizures, you see changes in synchronization, depending on how you do that. And it does not necessarily mean that you have a synchronous behavior, because this is synchrony. The synchronization is the active mechanism, and what you observe is synchrony. And this is something that is mostly mixed up in the literature. And also if you discuss with other people, they speak about synchrony, not about synchronization. Yeah? So this is a dynamical phenomenon, not a state. This would be the final state that we reach. But we are in some system that is highly non-stationary, everything changes. It's a non-autonomous system. The 4 standard forms of synchronization. Identical in the limes for large enough times, or lag synchronization. One system lags the other, or you have phase synchronization. In that sense, it could even mean that the amplitudes are highly uncorrelated. Yeah? And this one here, the classical definition by Christian Huygens was that it is constant. And if you have noisy systems, if you have chaotic oscillators, then you would need to find some kind of a boundedness, whatever this is, yeah? For real-world applications. So from all these different concepts, there's another one which is just called some kind of an interdependency, and this is generalized synchronization. That means there's a mapping between the 2 state spaces. That's it. That was believed to be the 4 basic forms of synchronization. Unfortunately, what happened? Push the right button, sorry. There is much more. Even if you only consider 2 systems that are interacting, there could be intermittent lag synchronization, imperfect, almost, noise-induced, anticipatory. We had some talks about that. And if you go to networks, then you have other forms of synchronization for which we even do not know how to characterize them. I think at the moment it's something like 21 different forms. And for each of that, you have different observables. For each of that, you need to go for different time series analysis techniques. So if you set up your ideas about how to study the brain, you would also need to make up your mind what kind of synchronization do you consider. Because that also then defines the way you treat that. Yeah? And there are always approaches to unify that somehow. And then a couple of weeks later, somebody comes up with a new form, and then, okay, forget about that. We start from scratch. Time series analysis. whatever is your favorite. There are lots of works to be done or that you can use in order to characterize some kind of an interaction coming from some kind of statistical approaches. This is, of course, the most easiest one, and this is probably also the reason why everybody does that. Yeah? You are studying amplitude relationships. I mean, you can also derive some phase time series and then study the correlation between phase time series. That can also be done, of course. Yeah? But it is the idea behind that. The first one is amplitude. Time-frequency domain is nothing else but some kind of a transformation. If it's easier to go from the power spectrum and then derive something there, or even higher order spectra, do that, fine, or you stay in the time domain. It's some kind of Augusto. Yeah? Information theory, this is also a big field where people said, I don't care about what it actually is. It is some kind of an information flow. I don't want to characterize it. It's just bits. Fine, do that. Yeah? But be aware that there are limitations on that. State space-based approaches. This is everything that goes in the direction of generalized information. And then people use Kramer. Now, it is something that is emerging. Everything which is above Kramer's Moyal assumes, apart from the statistical approaches, that you have a deterministic system. If you can decompose that into a deterministic part, a stochastic part, you take the Kramer's Moyal expansion, then you need to study something like interacting random dynamical systems. This is not even available in mathematics. I know 2 people who work on that so far. In terms of applications, you need to take into account that you might have variations in the different types of dynamics and the different forms of interactions, in the different forms of synchronization. There is nothing like a Swiss Army knife that can measure everything or assess everything. But you would need to take beforehand and say, this is what is interesting for me. Robustness against noise, measurement errors, speed of computation, if you have large amount of data to be processed, if you want to go for real-time applications, make your choice. Yeah? But be aware, it might give you something else if you go for another technique. And then comes interpretability. Particularly if you go for techniques that allow you to identify some kind of directionality, because people then very quickly go in the direction to assume that you can identify causal relationships. We are not talking about causality here, not in a physical sense. Yeah, this is more flow in one direction than in the other direction. It's mostly some kind of a relative indication, but not a clear-cut indication of a causal relationship. There are many influencing factors that would need to be taken into account. So some of these approaches that have something. If you go for phase dynamics, there are many techniques to derive phases from the recording. For example, the Hilbert transform or the wavelet transform. Mathematically, they are different, but they give you mostly the same findings. From that, you have different ways to identify the strengths of an interaction by, for example, the phase locking, the idea from Christian Hörens, the direction, that is some kind of a perturbation approach. One phase affects the other. And just recently, people also identified some ways to identify a coupling function. So that would be the only approach where you have all 3 characteristics. Yeah? Information theory allows you to identify mostly the directionality due to some kind of an asymmetry in the different estimators that is due to in Granger causality, mutual information, transfer entropy. They all have exactly these approaches. If you want to do strengths, there's so far as I know just one way to do that, which is the changing tendencies of generalized synchronization estimated with entropies. That's it, for generalized synchronization. This is a very strict ansatz that has been made there. The state space techniques, nice, yeah, from the concept, but you would need to reconstruct the state spaces from single time series. So what is a good choice of embedding parameters if you do a Tarkins embedding? Not easy. Yeah? So either you fix everything and say, okay, I continue with that, then you might find something. They can do strength and direction, and you get some properties of a functional relationship, some of them. If you relax many of these assumptions, then even this is lost, because then you don't assume the existence of this functional between the two state spaces anymore, and then everything is lost. So this is only strength and direction. That's it. This is something that is being used. I don't touch upon the others because this is experimental side. People are currently developing this. So this is mostly bivariate. If you have n interacting systems, why do you compare always pairs? Why not all of them in some kind of a consistent manner? There is something available. This comes from random matrix theory that has been lost partly. People forgot that. And go back again to the pairwise structures. There are some kind of multivariate autoregressive models that can do that in some sense, but that's it. And you need to ask, how reliable is that? Because this is so rare, you don't really know if this is something that is good for your approach. It might be something that has been especially designed for just this kind of application. Yeah? So the true multivariate one. You would also need to take into account that there is, particularly also for the pairwise ansatz, you know that if you just take two subsystems, and there is something behind this one that makes some noise, but you don't observe that, it has an impact on the two systems. If you don't observe the one that is making this noise, you have no idea what this is. So this is some kind of an indirect interaction. There are, of course, ideas to get that out. This is partialization. We know this from the partial correlation coefficient. And for all the other, mostly all of the other techniques have now an extension to partialization. But I will show later on, I make a remark on that this does not help. Another aspect that we need to take into account. We have said nothing about what is the node dynamics. There could be different natural frequencies, there could be different noise contributions, there could be this, there could be that, there could be different dimensionalities. So something that allows you to distinguish the different dynamics. This is nice. But you need to take into account that whenever you have something that differentiates some from the other, it lets you go to the effect that you assume that something that is the more active, the more noisy, the higher dimensional systems is always the driver. Go back to your data, just look at how noisy is these data, and if you identified a driving system, it is probably the more noisy one. If you don't know the underlying coupling structure, don't trust that. Of course, you need to take into account the finiteness of the data, the limited observations times that you have, any kind of univariate properties like the power spectral contents, and so on, the different time scales. There might be some kind even of a bias due to the approach that you have chosen. Something that would need to be taken into account. You could even have some kind of incomplete measurements. I mentioned this then just with this example here of somebody that makes noise in the background. There might be many other phenomena that have not, this is not on this list, yeah? But this is something that has been identified already as a confounder. So once you have that, you have set up your interaction matrix. Now you say, I have binary adjacencies. Good. Make up your choice how to go from an interaction matrix. You have a matrix that consists of some numbers. Depending on what, it could be real, it could be imaginary numbers. You need to find some thresholding. There are 3 criteria that you find, or 2 criteria that you find in the literature. The uniqueness needs to be defined, and the reliability means how reliable is the estimation of a given link. What does this actually mean? And if you look at the criteria that you have there, this is thresholding, which is mostly like that. Yeah, and then I'm done. Or you set some edge density or link density or whatever you are doing there. Yeah? And there's also the other idea of significance testing. This is nice if the networks are not larger than maybe 20 nodes. Otherwise, you will end up with a huge amount of comparisons. You need to control for that, for this multiple testing problem. And if you really go to large networks, I mean, thousands of nodes, no chance. So far. This is an unsolved issue. This is also the reason why many people go away from a binary representation of networks to the weighted one, because they know this is a problem. If you go for a weighted network, the whole story gets even much more complicated. The different dependencies that pop up here. So you have some kind of an estimated strength of an interaction. So the coupling, the strength of the coupling, this is something that you have estimated with your time series analysis approach. That depends on the true coupling strength that you have. You assume that there is some kind of a relationship. That might depend on structural properties of the network, of the underlying network. We know that. We had this example. You fixed the coupling strength. You change a little bit the rewiring probability, and the networks will synchronize without changing the coupling strength. Yeah? So this is not easy. There are probably many other influencing factors. We don't know how this dependency looks like. We assume it is there somehow. Yeah? But if you have this dependency, how do you define then weak and strong couplings? I will show you one example later on that this is actually not easy to do. Yeah? So and then you need to ask, what are the non-trivial properties of the data that are captured by these network measures? Because what we do now is some kind of overkill. We go from some time series, and then we make networks, and then we do this and this and this and this, and then we end up with, there was an oscillation in the data. You see that. You don't need that. Yeah? This is the idea that comes, of course, from the Kuramoto observations, that you have some kind of a transition when you increase the coupling strength, which is here on the x-axis, and then you have some kind of an estimation for the strength of an interaction, and you see that there is either some kind of a linear increase, there could also be some kind of sigmoidal increase, there could be some kind of a jump, like what you observe in explosive synchronization. We don't talk about hysteresis effects here, it doesn't matter. Yeah? So there is something that goes from an independent to some kind of a more or less dependent on-off synchronized, intermittent, to the strongly synchronized state, to the identical systems. Which is the underlying function of your system? Do you know that? Can you probe that? What you have is, you are sitting here, and from that, you would need to tell if you have a low number, does this really indicate weak coupling? Yeah, if you have explosive synchronization, the minimum here is much larger. It covers a large range of coupling strengths. If you're up here, is this already the maximum? If you continue with that, there are many systems that desynchronize again with increasing coupling strengths. So what do you have actually? What about common sources? What about if you have an impact there? There are, if you go for phases, if you look for phase synchronization, there's this concept of the mean phase coherence, which directly relates to the Kuramoto order parameter, only in time, estimated from phases for data. We know that this is prone to some bias. And people then propose something else, namely the phase lag index and the weighted phase lag index. You see, you'd go from the exponential representation to the sign, or some kind of a normalized sign. Good. We can simulate experiments. You assume you have two subsystems. Like that, you have subsystem A, subsystem B. The ideal configuration would be that you have each of these black dots represents a sensor. It is sitting exactly in the middle of this subsystem, whatever this means. Yeah, so it somehow measures this optimally. You have some kind of a sphere of influence here. So if this is placed correctly, then this sphere of influence here would just measure system A. That one here, under this condition, would measure a mixture of two systems. You can simulate that by measuring some kind of a mixing or a superposition with these alpha here, just to see how these different signal contributions, how these can be separated. Can we do that actually? So different systems, Rössler-Lorentz system. We did this also for other systems like Kuramoto systems and so on and so on. And what you see is that if you go for the Kuramoto, you make a zero coupling and you increase only the overlap, and you see it gives you an indication of synchronization. It's not there. The systems aren't coupled. Yeah? If you go away from the exponential representation, you go down to the sign or the normalized sign, this is done. It's fine. Makes sense. In models, it works. Yeah? It is robust, and so on and so on. We have done many, many things with that. It works. If you take these approaches now and go for real-world data and ask, if you go for that one and you go for these two, and you ask, is there an improvement? It has been designed for getting rid of a bias that comes from a common source, from overlap between different recordings. Can we really get rid of that? This is 20-hour recordings, 20 hours intracranial recording from just one subject. Doesn't matter what this is, but it's nice to have that because we have reference electrodes that sit on this grid here. We have the seizure onset in the grid. We have a lesion in the grid, covered by the grid. So we have many changes, many influencing factors there. This is either the pathology, the reference electrodes nearby, the seizure onset zone nearby, so some pathology, some structural pathology, everything is there. Yeah? And you can see that here on the left side, the upper part is the average of all phase synchronization measures over these 20 hours time range in 20 seconds windows, moving window. And what you observe here are these stripe-like structures. These are the reference electrodes. This is the epileptic. These are the boundaries of the next row in the electrodes. So it's something that transmits into this domain. And whenever you have these white structures here, these are related to the lesion and the seizure onset zone. If you go to these corrected versions, you still see these stripes. It's not gone. It's minimized. Okay. On average, looks nice. It's minimized. What about if you go on a temporal resolution? If it's just a minimization, you would expect that if you have a bias and that oscillates at some whatever level, and you correct for these bias, you end up, of course, with a floor effect or with a ceiling effect, depending on how your measure is being defined. If it lives on the unit interval, it might be that you don't see anything. Good news is, even if you have something that is somewhere between 0 and 1, if you look at this temporal evolution here and that one here, this does not resemble the one. And if you go for all of them, it does not resemble the one. So we compressed this information. We looked at the power spectra of these time series. And then there's a test for a comparison of power spectra. And what you observe is that the power spectra are identical exactly at the recording sites where you have the influence. So it does not help you anything. Directed networks. Same problem. You estimate the direction somehow. Whatever you do, it's Granger causality, transfer entropy, your favorite, you take that. This depends somehow on the coupling direction that is in your system. If you don't know that, you might end up with true, false indications of a direction just because of something. Then this something could be, again, some kind of a structural property, the coupling strength, the node dynamics, many, many, many other aspects can go into this relationship. If you don't know that, what do you learn from that, and how can you model that? Yeah? You need to resolve the correct directionality. This is the problem that you have here, and you need to distinguish this directionality. I will show you this plot in a minute, for different coupling regimes. Because now you are sitting again on the experimentalist side, because this is the data from something that is not known. And you need to again ask what are the non-trivial properties that you capture here, because you would like to go for networks. Typical setup, again, we have a system, we have two systems that are coupled together. Here's an increasing coupling strength. S is the estimate for the strength of for the interaction, and D is direction. Yeah, I used here the normalized form just because, just to show it could go up and down depending on how you define direction. So you see that already. You are sitting here. This is something that you have estimated. Now you need to ask, if I'm sitting here on that curve for the direction, is this coupling strength or that one? So that could give you an indication about systems are weakly coupled or strongly coupled, if you don't know the coupling strength. Yeah? So what you would need to do is always evaluate strength and direction. If you would like to make some claims about directionality, what kind of underlying coupling structure is this? If you only have one observation, don't do anything. Yeah? It can fool you. This relationship can be observed. This is data here from a study where we used, I don't know how many data that was. Just take all the data from different estimates of strength, direction, from different subjects recorded over day. This relationship that you see here is also reflected in data. It is there. Yeah? You just need to pull it out. Indirect interactions. Yeah? So the concept is you have a direct interaction, it goes like that, and then you take, for example, the Pearson correlation coefficient, and you are done. Yeah? And then you have this observation here. There's another system that you have not observed. You have non-interacting system, and this unobserved system introduces some kind of a spurious interaction into the systems. And the idea was to go for the partial correlation coefficient. Good. Old stuff. We know that. There are similar approaches for others. This is the partial directed coherence, the partial transfer entropy, partial phase dynamics, and so on and so on. All these techniques, even the concept of partialization, comes from an induction over n approach in mathematics. It was shown for 3. It was shown for 4, it was shown for 5, done. Nobody went up. Nobody went up. And then we did this in a bachelor thesis. Can we go higher? And it turned out it goes roughly up to 8, 9, 10, depending on the networks that you have. If you go for more, everything breaks down and you don't see these differences anymore. Unresolved issue. Nobody touches upon that, but it is there. What kind of network sizes do you typically have? Minimum 20, maybe some 100. Sorry. Another aspect, delayed interactions. This is just one example, again a recording. Here we study the directionality between different types of different channels of recordings or different recording sites or nodes within this network here during day and during nighttime. We know that there is some kind of an effect that comes from oscillations during the because of the biological variability. You can estimate that there is some kind of a delay within these systems in the order of a couple of 10 milliseconds. That comes from physiology, that comes also from anatomy. We did something like a brute force search because we don't know how to estimate delays in such systems. Yeah, so we assumed we have a range of delays, and then we try to find that. And if you then derive for example, here in that case, the symbolic transfer entropy from that, you will be fooled if you don't take into account delays. You end up with a wrong indication of who is the driver. Yeah? Something that needs to be taken into account. This is just some example here. Good. This is the holy grail where everybody wants to go to, namely weighted and directed networks. What you have then is an interaction matrix and you have a directionality matrix. That needs to be combined into an adjacency. And then you need to characterize that And if you look into the literature on graph theory for weighted and directed graphs, you mostly find nothing. Yeah, of course. I take the easiest one. Make it more complicated if as you want, do it. Yes. Yeah. So how to combine that? Let's assume you have done that. Yeah, you are done. You are famous. Now comes this question: how do you compare empirical networks? If you ask how similar are they, you can do something like group statistics, detecting of changes. You can go for temporal networks and ask, is there something? And then you ask mathematicians from graph theory, what is a good distance? Weierstrass, Gromov. You go into the prerequisites. Let's assume that, that both networks that you compare have equal size. Thank you. Go. Do you have something else? No. For what do you need that? Yeah? So you invent your own distance. You need to show that it's good. At the same time, somewhere else on the world, somebody else come up with a new distance measure. You fight, and we will see who wins. Yeah? As usual. But this is one of the problems that we have here. Yeah? And once you have this comparison, you would need to again go back and ask, what can trivially be expected here? Yeah? And is this really necessary? Is this whole approach really necessary? Because if you only capture some trivial aspects of the dynamics, then you don't need that. If you want to interpret that, there are, of course, then methods coming from bootstrapping, from null models, where you say, okay, I find some deviation from that one or that one, either from the lattice or from a random graph. There's also surrogate networks. There's a bunch of surrogate networks that had been developed over time. They do bootstrapping of networks by constraining different properties of the networks. That can be done. Everything is available. And you can also go down then, use the old concepts from nonlinear dynamics to see if if you can find some kind of an indication of influencing factors. You can also combine them. Then you see through a combination, if you start already on the time series level, you go on the different steps of the network construction scheme, then you see what kind of influencing factors are there. That can be done. Good. And then you end up here, and you see if the networks do not differ. What does this mean? Could be anything. Yeah? It's an issue of the methodology, it's an issue of statistics, it's an issue of whatever. You can go into the other side. They do not differ. And what does this mean? So far. Now, what's next? I mean, this is really destroying. I know that. Yeah. But I think it's worthwhile to do that, because many people use that, and then there is this idea, old stuff, I ignore that. Yeah, this is what many people do, they ignore that. Most people are not even careful when they use toolboxes. I use this because this is in the list of the clustering coefficients that I would need to estimate. This is always on first row in some Python package. Yeah, why? There is not a search algorithm that then highlights how many users it has, because it's just the first one that has been developed. And the others that are much, much better come at different positions. In many cases, because we have all these influencing factors, it might be advisable if you only interpret changes, and only that. Yeah? Not the network as it is, but if you see a change in time under different conditions, that might be more interesting and might also give you more information about structure-function relationships than looking at the properties itself. You would need to test inference sensitivity if you have some kind of models, do numerical simulations to know what you have done. At least give you some kind of trustability. And when you do that, you would need to model system dynamics and the observation process, because the observation process induces specific topologies in the networks. Good. So this is then the call for improved methodologies. Do that. If you know that, there are ways to do that. Yeah, but that needs to be done. Otherwise, we run around in a circle because everybody uses the same shit. Once you have done that, and you know all the influencing factors, you can go now for some characteristics of the theory of the network theory of epilepsy, and I will just show you some examples about what we discussed already, just what can you do others, what Hitten had said yesterday, what else can be done if you go for these graph theoretical approaches. This is a study where we compared data from healthy subjects and epilepsy patients with different modalities, EEG, MEG, under different conditions, IOs, eyes open, eyes closed, weighted networks, random binary networks, with frequency decomposition, without frequency decomposition, different measures, so the whole battery of what you can find. And here I show you some finding, which is what you can read in the literature, namely that epileptic networks are more regular than healthy ones, if you go for cluster coefficient path lengths. And you see it depends on the way you present it. This is here now in the delta band, and you find differences. Good. Then you look at the time series, and then you see the time series of the path lengths, for a weighted network, for a binary network, for a corrected one with the reference to a random network. And then you sometimes see that you have, there are dependencies. The construction rule, the network type, recording type, and so on and so on. Many influencing factors. And then we try to group that, and then you find that one here. I don't go into these details. You see this is not filled. Yeah? But what you see here, depending on how you do something, then you see in this condition, these networks are different, and in that condition, they are not different. But that depends on all these different influencing factors. Now you choose from one that is on the list, you go into the literature and ask, they have shown that, and then you go back and check, this is done with a weighted network of that frequency, that type, blah, 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 and you find this, you can find these findings. It reflects only the way networks have been generated, nothing else. It has nothing to do with the dynamics. This is what I meant with the trivial properties. Yeah? This cognition can modify networks. We had some discussions about what is a good way to measure changes or the impact of cognitions or other influencing factors. Here we do some very simple scheme, which basically consists of rest conditions. We let the subject alone, they can do whatever they want there. And then you have some tasks here. The first one is you have to learn something. Then this is a frequency fluency task. You have to generate some words or something like that. Again, a rest phase, and in this phase here, people are being asked to recall what has been learned here. Yeah? This is here an incidental task. So somebody reads the number of words that you need to learn, and you need to learn that, and afterwards you are being asked, what have you learned for that? So we have some output of the system. Yeah? The capacity of memorizing something. Same here, intentional. One is a direct task, the other one is you solve a riddle, and then you are being asked what was the solution of the riddle. Very easy. Yeah? There is no task like learning and recall, but it's just something that goes on the fly. So 13 patients, 20 controls that we have here. We have the number of recalled words as the output from both of these tests. We go here for a binary network, we measure clustering coefficient path lengths, and then we see that there is no change in the clustering coefficient, in the path lengths. But if you go for average statistics here, then you see that there is a tendency that the cluster coefficient increases the more complicated the task becomes. Yeah? And the funny thing is, when you reach the more complex state, namely the intentional learning, then you see that there's also some relation. Can you see that? Yeah, here. There's also some relationship with the recall performance. The cluster coefficient is measured during the learning phase, and then it predicts how much you can recall a couple of minutes later. I have no idea on a long time scale. This is, of course, within the setting, but it shows that there is some relationship between some cognitive measures and some reflection in the brain dynamics in these networks. What's going on during seizures? What you see is that there's always this concave-like motion. This is here data from 60 subjects, 100 seizures, and the functional topology of these networks goes from a more random to a more regular and back to a more random one. Okay, that could probably reflect the synchronized states that you reach there, and then you ask how stable is this synchronized state, and you use, for example, synchronizability, and you see that it becomes less synchronizable during the seizure, which is probably this effect that we have seen, that it is not a mechanism, that synchronization is not a mechanism for seizures to start, but a mechanism for seizures to end. And if you do, if you measure the assortativity of these networks during a seizure, then you see that there is some slight tendency to increase depending on how you measure the assortativity. Here we have used different techniques, different concepts of how to do that. And what you then find is that because of this tendency to go up, these are harder to synchronize. They are less vulnerable to attacks. And this is also something that the clinicians know. If you have a device that tries to disrupt the ongoing seizure, you need to do this at the very beginning. The further you go into the seizure, it will become harder and harder and harder to stop that, which is probably a network mechanism. We heard about this concept of this epileptic this epileptic focus. If you set up a network and you say one of these nodes is the epileptic focus, you can ask very simple questions coming from sociology. Is this important? Now, there are many concepts that are called centrality, and with centrality concepts you can ask for the importance of, in terms of it is highly connected in a functional sense, it is a bottleneck, it is this, there's a whole spectrum of different centrality concepts. Here we used just a few of them, namely strengths, eigenvector, closeness, and betweenness. And here just some examples. Here what you see here in the different colors is either the centrality of at some point in time during the seizure, the centrality of a node or a bunch of nodes that would be related to the epileptic focus, its neighborhood, and the rest of the world. And what you see, and this is what most people do, that they use here some kind of a concept with strengths or connectedness or connectivity. In this case, there's not a big difference. The focus is not important. It becomes important if you look for some other structures, namely what is the impact on the whole network? Will it generate some kind of a bottleneck-like structure? Then you see that it's coming up only at the end of the seizure. Then there is some kind of, now it relates, of course, then back that how does it stop? It needs to go back. There must be some kind of a synchronization between then this epileptic focus and the rest of the network. Then it stops. What about long-term changes? I mean, I mentioned already that the biological rhythm have an impact, and they also, of course, also have an impact on networks and network characteristics. And here's just one example of a subject where we had data over something like 11 days. Whenever you see your red lines, you see that there were seizures. And what you see is that there is some kind of rhythmic-like patterns in the clustering coefficient and the path lengths. And if you look for the power spectra, then you see that there are power spectra of these time series here. Yeah? Then you see that there is strong impact of circadian rhythms. For this global network measures, yeah, which capture the gross dynamics of the whole network, it is probably not good to look for seizure precursor that are local in this network. So a global characterization does not make sense in that case, because they would live down here in these regimes. And you see this is orders of magnitude below these fluctuations that you have in the, just due to biological rhythms. You will find that if you go for local characteristics, like for example with different centralities for links and nodes. There's a paper coming up soon. Assortativity and dissortativity. This is also fun to see that the descriptions that you find in the literature, namely that neural networks are always disassortative, is not true. It depends on time of day. Yeah? Again, you see, not in all cases, but in that case here, you see some kind of a relative change. It goes up and down, and if this change is somewhere around the expected values for a random network, then you see it has some fluctuations into the assortative regime, but also into the disassortative regime. Yeah? On average, or you take just snippets of the data, then you can make some claims about that. But if you ask how does this look in the full spectrum, it is not that easy as many people expect. This is a scheme that we proposed just recently in some abstract space, namely a space that is spanned by the path lengths, by the clustering coefficient, and the synchronizability, particularly now for for networks of seizure dynamics. And this is how these networks move in that space. So it's some kind of an fluctuation between integration, segregation, and variations in the propensity for synchronization. Now you can ask, where are seizures located? In which kind of these weird trajectories that you see there? And it somehow makes sense that you have a change in synchronizability during specific times of the day where you then also observe seizures, and not at other locations. Something that can be identified if you have some more global characterization of a network. Good. What's next here? Hitten mentioned that already yesterday. We need to improve first the sampling of the epileptic network. We don't know what it is. I mean, we know what it is. It's the brain. Yeah? But we can't sample the whole brain. And the question is, what if we have accessibility problems? What would be the minimum required assessment of links and nodes in these networks? There are lots of other technologies that are being developed. For example, link deletion, link detection. Whenever you have other types of networks, if you miss some links, you might find them from the dynamics, and then you know that it can be there. You can also go for the other way around. We have proposed some technique here for a link deletion technique based on centrality whenever you have an oversampling. It is effectively some kind of a tiny network perturbation. You remove one link, and if you don't need it, it does not change the overall topology of the network, throw it away. You don't need that. Yeah, it's just some kind of ballast that you just carry around with you. We need, again, from the sampling, then the characterization of these networks. This is something that needs to be done. So far, this is looking for the standard graph theoretical tools. There's already a little bit of developing of new concepts, of new tools, but this is not the end so far. Yeah, so there is room for improvement, much room for improvement. At the final idea would be then that you have some kind of an epileptic network-based prediction and control, which means you have some ideal sensing system that records, that does some kind of an online screening of precursors, of resilience, stability, whatever you have there. And it should also then give you, from a much more global characterization, some idea about how to perturb that. Yeah? Mitten mentioned it yesterday. What is typically being done is node removal. This is surgery. There's one technique that has been developed in the 90s in Bonn. These are subpile transections, where you just disconnect a brain region. That is forgotten. Yeah? That would be, for example, a modification of links. And then, of course, that there is also the idea that you can control the whole network. And now also there are some kind of ways, Itten will touch upon that in a few minutes, namely some kind of activation of the brain that are diffuse, but they assess the whole brain. For example, the vagal nerve, if you stimulate that. The idea would then be, if this is some kind of an ongoing loop, and you'd have this measurement, control if it's necessary, prediction, maybe also if it's not necessary. This is the question that you have here. The idea would then be that you have some scheme like that, that the system, when you start with such a perturbation or with such a control, you have probably some kind of a modification of the network. On the long term, this modification might go into different states or stages, and the idea would then be that the transition into seizures is then over longer time scales fading out. This would be some idea of how that could work if you base that on a network concept. And then you have indeed some kind of new therapeutic options. And because there is this high variability, that would probably go into some kind of an individualized treatment. I'm done. Thank you. Before we have some discussions, of course.
Thank you very much. Thank you. Beautiful talk. Very, very instructive. Questions, please? Yes.
Well,
go ahead.
During our discussions, I feel like hope is kind of fading in neuroscience.
No.
I don't know.
No.
What I want to ask is that what kind of advice would you have for young scientists that look at this methodological panorama and somehow feel that we are lost in math and producing new dead salmons?
No.
In our field.
Yeah, yes, exactly. The dead salmon. Yes, good. No, advice would be question yourself. I mean, this is natural science, what we are doing here. You need to question yourself. Don't trust what you have, and don't trust what others have been proposed. Just look at the prerequisites, what is behind that, and then you will see that if there are too many assumptions, do something. I don't know what to do, because that depends on your system. I mean, for the brain, we discussed this already with the dead salmon. Yeah, this is exactly going in that direction. Yeah, it was too long that people just trusted what is going on there, and then there must be one critical experiment, the critical experiment. This is the critical point. Yeah, do it and show it will not work, but then come up with something else. Sorry, Hilda. For this network aspect here, yeah, for the neurosciences, in terms of cognitive neuroscience, this is stable. Yeah, what you find there is that the whole variability of any kind of characteristics is extremely small. Yeah, what we see, the variations that we see here are due to the pathology. The pathology brings this unobservable range into something that can be observed. And this is then nothing else but some kind of a relative deviation to what is normal. You would probably have not all these issues, yeah? But you might find them. And then, if you know it, do something. Not just thanks, and then go home, do something.
May I comment on his talk before we go to some others? As up until now, there had been essentially three groups. One are the medical doctors who, don't like to accept that sometimes they have made a mistake. Then there are the physicists who are not as hard as the medical doctors, but they are there. And then the data, the analysts who have their own ways to do things. So my impression here is that we need to look at the big problem in a completely different way. And the only thing that it occurred in my mind completely different is, why don't you, in some group where they have a good group of analysts of all kinds, call teenagers, early teens. You call early teens that are good in solving puzzles, because they have to be able to find these little differences. So, and then you just give them, a thing in which they start looking at the problems, and if they find something, they tell you. They may be able to suggest something. So suggest some way of looking at the problem, which may be good, may not, but it's a completely way to look at it. This wouldn't be the first time that some problem had been solved because someone has a good eye to solve puzzles. Okay, so
Marcus.
Sorry, let's go to the next. Who wants to? Yeah, he.
Thank you for the lecture. Would you mind going some slides back? I have a question on when you were defining. Stop. Yeah, okay. When you were defining the interactions. Okay. This one. Yep. Yeah. So I'm a bit more used to ecological interactions, and I've seen a lot of direct interactions, indirect interactions, and recently I've heard of what would be like, it's not exactly a third thing, but it would be of invisible interactions. Yeah, which, for instance, like there is like a flower and a butterfly, and they only couple once, and like it's once in a lifetime, and even though you can have like the best equipment to measure it and everything else, and you still won't get this butterfly, for instance. But this interaction still happens. So, I don't know, I feel like, at least for neuroscience, I'm not familiar with, but I feel, what are the tackles to investigate those kinds of invisible interactions, and also how do modeling affect it? Yeah. Because are the models effective to how can I say, to predict, not predict, but to understand those interactions? Are they able to do it? Okay.
Nice question. Of course. Behind all of these techniques is the assumption that the coupling is constant in time. If you have something that pops up and goes down, and even if you have some kind of a driving force behind it, you will not see that. It's always the assumption of constancy. What you are going into is non-autonomous systems, where you have systems where everything is time dependent. Have fun.
Another question here.
Thanks for the lecture. So I have two questions. The first one.
Excuse me, put it in the front like that.
Yeah.
Yes,
Like
because otherwise we don't.
Okay, thank you. So the first one, it's simple, which you mentioned the term that the driver in EEG recording or brain. So what's the definition of it? And the second question is more generalized. So for the perspective, viewing brain as an adaptive system. So for mathematician or physicalist or neuroscientists, is there a unified perspective to define it, or what's the difference of this kind of modeling? So.
Sorry, I didn't understood the last question. That was a little bit too much. Model. Can you repeat that again?
Yes. So there are a lot of people claiming we are treating brain as an adaptive system.
Okay.
Yes. So we are like from different backgrounds, for mathematicians, physicists, neuroscientists. Is there are they have different definition for it, or they have a unified?
Okay, now I got it.
Yeah.
Okay.
You.
First question, driver. This is the brain region that exerts most influence onto other brain regions because of whatever. Yeah, that could be some kind of a connection. That could be because I am the strongest one, and because this is an epileptic focus, or it doesn't matter what it is. Yeah, it is some kind of in a physical sense then a drive response system, and something starts and the other ones follow. Okay. Yeah. In epilepsy, there is some kind of a concept of a focal driving. People think that the focus is something like that. You would need to show that it's really like that, because it's just some feeling, some gut feeling. It looks always like that. If this is really true, is not known. Adaptive systems definitions, take his definition of an indirect link, or what? Yeah. Whatever. Yeah. So there are so many different names coming from observations about how to bring that down to something that is unified. We are not that yet there. This is too early. Yeah? Because this concept of using networks, I mean, this is 25 years old now. If you go back to Euler, this is several hundred years old. It doesn't matter, but that the application is there from graph theory. And you do something, and you study different types of systems, and you see there are commonalities. This is what is fascinating. But then you would also then need to get the different languages that you have into some kind of a unified way. Mathematics can help by that. Yeah? But what you typically observe is that people generate their own language. Butterflies, whatever. Yeah? Not yet, but it needs to come back.
There is another question.
Klaus, you talked about there being a couple of failed attempts at a unified.
Can you hear him?
I go up, doesn't matter.
No.
You talked about there being a couple failed attempts at a unified theory of synchronization, and I wonder if you can talk to us about any of those, and if there are any that are promising or that are new, and what it means to be a unified theory of synchronization.
Not yet. Not yet. As I said, the point is there is, we have some basic concept that were the first four that I showed, and that might work. Yeah? And even the people that developed generalized synchronization, it was called generalized synchronization because everybody thought, now we have it. Yeah? The way from identical via lag, via phase, via to generalize makes somehow sense. So that scheme that I showed there. Yeah? Can you go back? If you turn something off, you will then go to whatever kind of synchronization. It did not work. That was one of the first tries to unify that. 2 weeks later, the experiment showed no. Another 2 weeks later, no. Many counterexamples. Next unifying theory. After years. Yeah? And then came all these lists of what we currently have, also these different types of synchronization. If this is just an expression of something that is much more fundamental, we don't know it yet. Yeah? Because all these different aspects that we observe on networks, you keep everything constant and you change a little bit the topology and these networks will synchronize. Yeah? It is too early. Not yet. Yeah? Build evidence for that. If you have take your data or your observations, your research field, you will probably provide some evidence for different types of synchronization that would then need to go into these definitions.
Okay, just before we go to the break, Hilda wants to show us.
No. It's not related
Ah.
to this, but it's related to the to the school. Yeah.
Ah, but you want to do it now?
Well, no, first let's thank.
Yeah, sure. Yeah.
Thank you.
Yeah. Can you contact the CNN in your